Hey, welcome back. This is 8.2. Now we're going to be looking at graphs of functions. We've already worked a little bit with some graphs previously when we were graphing equations of lines. This is just an extension of that. So functions represent more than just straight lines. As you see there in the picture on the right, we have this kind of V-shaped graph. Our first quest is to figure out if given a graph it is a function or not. We learned last time that a function is a set of ordered pairs where each x-coordinate only goes to one corresponding y-coordinate. And in this new setting, you could tell whether or not a graph is going to fulfill that requirement via what's called the vertical line test. Okay, so that's kind of where we start in this section. The vertical line test. And it basically says that if you draw a vertical line anywhere and it only hits the graph in at most one place, then it is a function. So there's my attempt to draw number one. And basically, if you draw a vertical line and it only hits the graph in one place, like there, there, and you have to consider every possible vertical line in the universe. So long as each one only hits one place, then it is a function. So this is a function. And you can kind of see how this corresponds to our previous definition. Here, this would be an ordered pair, like 1, 5, right? And because it doesn't go through any other points on the graph, there's no other 1, something. There's not this extra ordered pair in our set that's going to have the same x value but a different y value associated with it. Okay, so it's pretty easy to apply. Here, number 2, that's definitely not a function. Kind of looks like a greater than symbol. We'll be talking a lot about greater than or less than symbols later on here. So if you drop a vertical line right there, it hits it in 2 places, so you're done. I mean, in other places, like if I dropped a vertical line right here, it only hits it in one place. But again, you have to consider every possible vertical line, and if it hits it ever in more than one place, then it's not going to be a function. Okay? Not a function. And it's literally a visual thing. You could just look at it and know. Number 3 is a little tricky. It's just a horizontal line. And of course, if you drop a vertical line anywhere onto this horizontal line, it's only going to hit it in one place. So it is a function. This is a function. So it's a bit weird. But you can get graphs that are like this. So the circle is probably the best example of a familiar graph that is not a function, right? So if you have a circle as your graph, it's not a function. It's an important object, right? We see circles everywhere. You just go outside, you could look up in the sky and see the moon. There's a circle. But it is not a function here in the world of mathematics. Okay, so it causes issues, but there are ways to work with those things where you can kind of cut it in half and it'll be a function, and you'll learn how to do that later on. Okay, then we go on to kind of analyzing these graphs. And the first types of problems, you're using the graph to evaluate the function. So you see that up and down shaped graph there on the right. That thing is the graph of some unknown function. And we want to know f of -6. So what the heck is f of -6? Well, the x value is -6, and we want to see the corresponding y value on the graph. So you just go over to -6, and then go down. See if I can really quickly copy and paste this thing. Maybe copy image and then paste here. Where'd it go? Okay, it's being a jerk. But anyways, you go over the -6, and then you count down to where the object is sitting. This is really getting on my nerves. I can't believe it won't let me do that. Ticks me off. Well, anyways, if you look at -6, the blue curve goes down to -8 there, so the output should be -8. So you just read it off the graph. Very quickly, this is driving me nuts. Let me kind of just grab it because it's being a jerk, and I'll save as. Geez, I really got to go through all this. I apologize. This must be terrible for you. Jeez, really? Now we gotta find where to put it. You know, it's gonna take a half hour. Gosh, where's my? Oh, there it is. Spring 2023. 60. Graph. This is like 8.1 or something. 8.2. We'll just put 1. Save, and then we gotta insert file. Maybe I could just go insert picture. File. And then is this? No, I'm not in it. So I have to go to 965. Oh, there it is. And then, okay, great. So you go to -6, and then go down. It's this point right here, and you just find the coordinate for it. The coordinate is -6. The output is -8. Right. So there's our -8. That's why the answer is -8 here. Okay. Sorry, couldn't draw on the actual thing itself. Had to go through that crazy process. Okay, another one of these. So you're just locating, you know, the object. And then maybe I just found a quick way to do it. No, I don't think so. Oh, I got it somehow. I got it to work. I'm so sorry. Cut, and then copy, and then paste. And now it's doing the old one. Okay, so somehow copy, paste, and of course it's doing the old one. So whatever. All right. So anyways, you just gotta find the point on there at 4. So you go to 4, and then it looks like it's 2. The order pair is 4, 2. So number 6, f of 4 is equal to 2. Okay, so you just locate the point on the blue curve thing. So f of 5 here, you zoom in. F of 5 is 0. Hopefully that's clear. You know, I'll cover it in class if it's not clear. G of 8. Hopefully it'll be clear if I cover it in class. Let me do this thing again. So we'll just copy and paste. Two. Seems like a lot of trouble to go through, but there we go. Well, that took a little less time. So anyways, G of 8, so you just go over the 8 is here, and so it's going to be this ordered pair, which is at 8, comma, looks like -8. Okay. Another one. This one's a little bit odd, so very quickly, let me attempt my process again. I'll just save it as that. Yes. And there's our guy. So we want to make it a little bigger so we can actually see it. Okie dokie. So the question is, what the heck is G of 12? And the issue is that there's no 12 x value on this graph. But what they want you to do is kind of just extrapolate the direction of the line from the given information, right? So if you were to continue that line on and on and on, lots of technical issues today, like this, and you know, continue your x-axis on 6, 7, 8, 9, 10, 11, 12, the corresponding coordinate would be 12 comma negative 2. Okay, so you have to kind of guess based off of the information given and just do your best there. So I guess it's negative 2, even though I can't see the rest of the graph. That arrow kind of indicates it just goes on and on forever in that direction. Okay, so maybe it's an implied kind of notation. Another one. Okay, so this is kind of the reverse problem now. So I'll save, yes, insert. No, it's not going to let me do that. There it is. Paste. So the question for this one, for what values of x is g of x 6? So you want to find the x values now that give you the output of 6. So 6 is right here. That would, anything on that line would have a y value of 6. So there's that one point basically at negative 2 comma 6. So the x value there is negative 2. Okay, and now we're into interval notation stuff. So, all right. So they want you to put this. They want you to do two things with this interval. They want you to put it into set builder notation and then also graph it on the number line. I like to do the number line graph first. So what this represents is all the numbers in between 3 and 7, but you don't include 3, you do include 7. So if you have this parentheses like this or like this, it means don't include that number on the end. In your set of numbers. Okay, so you basically have a bucket of numbers. Anything in between 3 and 7, you can't include 3, so 3 isn't in the bucket. But you can include 7, so 7 is in the bucket. So if you see a square bracket like that, or the other directional square bracket, that means you do include the endpoint in the bucket of numbers, in your set of numbers. So they call the bucket a set. You do include the endpoint. Okay. So on the number line, if I were to graph it, so I have here's 3, 7 is over here somewhere. It's all numbers in between 3 and 7. So it's going to be all of this junk. So the number 4, for example, is in there somewhere. You could label all the tick marks if you feel so inclined, 3, 4, 5, 6, 7. But we exclude 3. So we're not, to indicate that, we use an open parentheses. You can use an open dot like this. So some books will have you do it that way. And then on the 7, you include it, so you put a bracket there. Okay, so that's the number line. For the set builder notation, you have to write this as an inequality. So it's all values x in between 3 and 7. So you use those carets to indicate that x is greater than 3. So this, x is greater than that. If you read it in kind of this direction, x is greater than 3. And then if you read it in this direction, x is less than 7. Okay. So this would indicate everything in between 3 and 7. And then to indicate that we don't include 3, or rather to indicate that we do include 7, we're going to put a little line underneath the second inequality. And then to indicate that we don't include 3, we don't use a line under the inequality. Okay. And then to do the set builder notation, we write it's the set of all x such that x is in between 7 and 3. Okay, so this is read as the set of all x. So the set is this symbol. So that's the set of all x is from here. All x. And then the bar means such that. Okay. So such that. And then that phrase right here, x is greater than 3 but less than or equal to 7. And that's it. Okay. So that's our set builder notation. They say all mathematics can be put in terms of sets. So if you're, the kind of the programming language of mathematics is set theory, is what they call it. And we can describe intervals in that way. It's kind of a little bit quicker than writing all that out. The set of all x such that x is greater than 3 but less than or equal to 7. So maybe some extra kind of definitions are in order here. So this x is greater than 3. Okay. This means x is less than 3. But you can also write it as 3 less than x. So that also means x is greater than 3 over here. So it's not like an equation where you could write x equals 3 and then 3 equals x. So you wouldn't be able to write x is greater than 3 and then 3 is greater than x. Those wouldn't be the same thing. You have to kind of, if you're going to read it in this direction, it has to be x and then the greater than symbol. And likewise, if you're reading in this direction, you kind of see x and then that you have a greater than in reverse. It's kind of hard to explain verbally, I guess. But anyways, on this side, on the right here, x is less than 3. To reverse it, you would write 3 and then greater than x. Or if you wrote it, if you read it forward, x, and then you see it's kind of a less than symbol in that direction. And then if you read it in the other direction, you have the less than symbol in that direction. So x is less than 3. So either way you write it is kind of the same thing. So if we put it all together, we have x greater than, let's say, -3, but less than +3. Okay. So this portion says x is greater than -3. And then this portion says that x is less than 3. But overall, it just means that x, and you can kind of see it visually, x is wedged in between -3 and 3. Okay. Then on top of that, you can include these lines underneath these inequality symbols, and they mean or equal to. Okay, so 3, let's write x is greater than or equal to 3. Okay, and you could also write that as 3 less than or equal to x. So if you read it in this direction, the inequality looks like a greater than or equal to sign. If you read it in this direction, it's still greater than or equal to. Okay. And then likewise, x less than or equal to 3. And you could also write that as 3 greater than or equal to x. But if you read it in this direction, less than or equal to, read it in that direction, it's less than or equal to, so it's good. Okay? And then you could wedge things in between so you could say x is greater than or equal to -5, but then less than or equal to 2. And it would just be all numbers in between -5 and 2, including -5 and 2. Okay. Just to send home this idea, let's look at some numerical examples. So is 3 greater than or equal to 3? Well, yes, and so it's asking is 3 greater than or equal to 3. So long as one or the other are true, it's true. So this is true because 3 is equal to 3. What about 4 greater than or equal to 3? Well, that's definitely true, right? 4 is greater than 3. It's not equal to 3, but it's greater than 3, so it's still true. On the other hand, then there's questions like, is 2 greater than or is it just greater than 2? No, it's not. 2, you know, if you 2 is not more money than $2. $2 is not more money than $2. So that's just false. Is 4 greater than 2? Well, yeah, that one then is true. Okay, so so let's get back to the story at hand here, and let's try number 12, and maybe it'll make a little more sense now. Okay, so 12, you have the interval from -3 to 6, including -3, but not including 6. So on our number line, here's -3, here's 6, and then this means all numbers in between -3 and 6. And we include -3, but don't include 6. Okay? As an inequality, you wedge x in between -3 and 6. And then we put the line underneath the first inequality because x can actually be equal to -3, because -3 is included in the set. Then to write it in set builder notation, you're just going to tack on this x and a bar and then some curly brackets. So it's read as the set of all x such that x is in between -3 and 6. X is greater than or equal to -3, but less than 6. Okay. So on the homework then, it's kind of already done the x and then the bar part, and you just write -3. You could use little buttons below for less than or equal to. The less than symbol is on the keyboard. And then push enter. And then you click on the appropriate number line. We said that was C. Check the answer, and then you should be good for the next one. Okay, number 13. We have the interval 6 to 9, including both endpoints. So on our number line, here is 6, way over here is 9. It's everything in between those two, and it's including 6 and 9. So 6 is in that set, 9 is in that set. As an inequality, we would write x and wedge it in between 6 and 9. Because we're including the endpoints, we use the lines underneath the inequalities. And then for the set builder, we tack on the bar, the x, and then the curly brackets. Okay? So this will be 6 less than or equal to x less than or equal to 9. Okay. And then the graph has to have 2 brackets on it. And we should be good. Okay, now we have infinities to deal with. So question 14, we want to the set builder notation for 2 to infinity, and we want to graph it. So on the number line, what does that mean? So here's the number 2. The interval from 2 to infinity is basically just going from 2 and then everything above it to the right. Okay, so the infinity, positive infinity is over here, and negative infinity is way on the other side. Okay, we don't include 2. And then with the infinity symbol, we always use parentheses. Okay, so that's why you see a parentheses on the infinity symbol. You can't include it. It's not like a real thing. Okay, so as an inequality, it's any x value in this interval, like 5 or 6, that is greater than 2. So you just write any x greater than 2. We don't include 2 in that. And then you go your bar x and then curly bracket. So x greater than 2, enter. And then on the number line, it's just a. 7 to infinity this time, so number 15. This time we include 7. Last time it would be like including 2. You know, we didn't include it this last time, but now we include that left endpoint. So on the number line, it's all things that are bigger than 7, right? So we indicate that with a bracket, and then like the number 9, the number 10, anything all the way up to infinity. And to write that as an inequality, it's any x value that is greater than or equal to 7 this time. So you have to put the line underneath the inequality, and then you tack on the bar, the x, and the curly brackets. So x greater than or equal to 7, check answer, yay. And then we could do our interval, yay. The other side of the coin, negative infinity to 3. Okay, so now this is a set of all numbers that are less than 3. So here's 3, and that's the set of anything that is less than 3. So anything in this direction towards negative infinity on this side. Okay, we don't include 3 this time, so we use an open parentheses there. And then as an inequality, it's any value less than 3. So 0 would work. You can do a test value, you know, -5 is less than 3, so that works. And then for your set builder notation, slap on the x, the bar, the weird parentheses, and you're good to go. Okay, so anything less than 3, there you go. Okay, this is the same thing, but with a decimal value. It works the same way. It's no big deal. Negative infinity to 2.6er. So there's our number line. Here's 2.6. So this just means anything to the left of 2.6. So anything over here. We don't include 2.6. In set builder notation, it's anything less than 2.6 / x, curly bracket, curly bracket. So x less than 2.6. Yay. Don't include 2.6, so it's D. Okay, now we're into these problems, identifying the domain and range from the graph. Okay, so I'm going to be copying and pasting these dudes. If you don't mind, just uno momento, por favor. Save as, save over, yes, and then we should be able to paste over here. Okay, all right. Let's expand it a little bit. Move it down a little bit. Okay, so this is numero 18. And we want to identify the domain and range. So the domain are basically all of the x values, all the possible x values that are associated to output values. So you can think of it as kind of like if I had a trash compactor that was smushing that number line onto the x-axis, then the kind of remnants, the blood, would be right there, right? And on the left, you're going to have some blood residue on. I hate to use that metaphor, but I'm sorry. It just is what pops in my brain. -2, and then on the left, there's nothing there because of that open dot means there's nothing there. Okay. Another way to think of it, maybe let's think of a more positive kind of way to think of it. Sometimes those weird negative ways are good for remembering, but they're a bit disturbing. Another way you can think of it is kind of a shadow. Okay, so you can draw a number line underneath our graph for the x-axis. And imagine the sun over top of it, right? So let me get rid of all this junk. And the sun is casting a shadow. All right, so here's my sun. And it's casting a shadow onto that number line below. Okay, so the shadow is like this all the way up to 1, but there's a hole at 1, so it's not going to include that. It's like the light passes through that, right? So it's you've got this light coming down onto that graph, and it's casting a shadow onto the number line. That shadow is your domain, folks. Okay, so let's make sure we got the right numbers here. -2, -1, 0, 1, 2. So it looks like the domain is going from including -2 all the way up to 1, but then there's that hole there, so we don't include 1. Okay, then for the range, you could kind of think of the same idea. You could think of the trash compactor smushing that graph onto the y-axis. Okay, that's kind of the negative way to think about it. A more positive way is maybe the headlights of a car. You know, you have some sort of, if you spend a lot of time driving like I do, here's a car, the front of it, right? There's the wheel, and then, you know, the occupant is in here driving. Hey, get out of my way. I want to get to work faster. And it's shining its headlight, and then the kind of shadow onto the y-axis that I drew over here on the right is what I'm interested in as the range. Okay. Okay, so if that thing casted a shadow, there's an open dot, so I don't include that part of it. It looks like that's at 5. And then there's going to be a shadow all the way down to -4, I think. And then there's a dot there, so I do include that part. So the range is going to go from -4, including it, because of the solid dot, and then all the way up to, looks like 5. I don't include that because of the open dot. So the domain is close bracket, -2 to 1, open parentheses. And sometimes you need a different way of describing the domain. If it's not like a solid interval of numbers, sometimes it's a bunch of points, a bunch of numbers. Okay, we'll see that later. But this time you could do both in interval notation. Okay, so the interval -4 to 5, close bracket, -4 to 5, open parentheses. Okay. Okay, so let's do another guy. Copy this dude. Yes. Okay. And again, it's this idea that I could just do kind of projections onto number lines below and then to the side. So first for the domain, you're doing the projection onto this number line below it. Okay. So here we have 0, 1, 2, 3, 4, 5, 6, and there's a closed dot at 4. So it's going to start there at 4 with a closed dot, in other words, a closed bracket, a square bracket, and then everything in it, that little arrow means it just goes on and on forever. Okay, so the domain is going to go from square bracket 4 on and on forever. That means it goes to positive infinity, and with the infinity symbol, you always use an open parentheses like that. Okay. Then for the y-axis, or for the range, in other words, again, we want to put in some tick marks. 0, 1, 2, 3, 4, 5. This is -1, -2, -3, -4. Again, I'm thinking of this kind of the shadow of this. If there's a car and it's shooting its headlight over there. Oh, there's a car. It looks like a car. The shadow of that then is going to go from 1, and then it keeps going up and up. And maybe it looks like it stops, but it actually is going to go up and up and up forever, because this little curve is going to just keep going up and up and up and up. So the shadow is just going to be everything up to infinity. Okay? So the range in this case is going to start at 1 and include 1 because there's a closed dot there. It's not an open dot. And then it's just going to keep going up and up and up forever. So it goes to infinity. Okay, so the domain, square bracket, 4 to, and then I go backslash INF, and then open parentheses. And then the range, close bracket 1 to backslash INF, parentheses. Okay. Okay, another guy. Copy over here. Let's see those. Yes. Insert. Paste. Let's make it a little bigger. Okie dokie. So again, it's the same deal. You want to see kind of the shadows cast by these things onto the number lines. So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the other direction, -1, -2, -3, -4, -5, -6, -7, -8. So the shadow cast is clearly, I think, going from -6, including -6, because it has a closed dot, all the way over to 8. So the domain this time, including -6, all the way over to 8, square brackets on both. And then for the range, 0, 1, 2, 3, 4, 5, maybe. Let's go with 6 to be safe. In this direction, it's -1. Okay, so it looks like the shadow then is starting at 0. It's including 0, and then all the way up to 4. Okay, including 4. So again, it's just basically the kind of shadow onto that number line there to give you the range. So the range in that case would be including 0 all the way up to 4. Okay. So square bracket -6 all the way up to 8, square bracket. And then the range, square bracket 0 all the way up to 4, square bracket. Okay. 21. Let's look at that guy. Let me get let me steal the graph again. I don't know why. It used to be just copy and paste. I don't know why it's being so sensitive anymore. Probably they have copyright issues or something. Anyways, again, it looks like we are playing the same game. It looks like it's going to be all real numbers for the domain this time. I must have hit the button on my pen again. I love it when that happens. There we go. All right, so there's this, and again, you're thinking, here's the sun, and it's casting a shadow, and in this case, it looks like everything, is being shadowed out. So the domain is everything, and to write everything, you're going to write parentheses -infinity to infinity. Then in the other direction, it's looks like all the way up to -3. So this is -3, -2, -1, 0 is here, -4. So it's all of this, junk is being cast onto the number line here. So including -3 and then just downwards to -infinity. So the range is going to go from including sorry, it's the other way around, right? You start, so if you were to lay this thing flat, you'd have to kind of lay it flat. It would look like this. -infinity is over here, and then, -4 and -3. It's everything below that. So you read from the bottom up when you're working with that vertical number line there. So from the bottom, it's -infinity all the way up to -3, and we're including -3. Okay, so the domain -\infinity. See the wrong symbol there. Comma \inf, and then parentheses. Yay. And then for the range, -infinity. So parentheses -\inf all the way up to -3. Bracket. And this is one of the ones now you're going to have to use the other kind of, the set builder kind of notation to get your answer. Let me grab it. Okay. Bigger. Okay, so on the x-axis, the shadow cast is a bunch of dots, right? So it's, let's get the number line going here. I think I only need to go to -3. I really only need to go to 4, but I'll go to 5. So when the shadow is cast, there's going to be a dot at -3. Underneath, and then there's a dot under -1, a dot under 0, a dot under 2, and a dot under 4. So to write the domain, you can't use interval notation. You have to use that other notation, the set builder notation. The way that'll work is you're just going to write x and then the bar like we did above, and then you're going to tell me what x is actually equal to. So you're going to say x is -3, and use the comma, -2, oops. It's -3, -1, 0, 2, and then 4. So that's a little bit different. -3, -1, 0, 2, and then 4. Okay. And then for the range, believe it or not, it's just one number. So if you consider the shadow onto this vertical number line here, the only shadow that is made from casting, if you think of, again, the headlight of a car casting a shadow, there's just going to be one dot on the number line at the number 1, right? So there's just that one shadow. And so to write that up, we have to, again, use the set builder notation. We can't write it as an interval. It's all values x such that x equals 1. Or in this, sorry, all values y, because you're talking about y coordinates. Okay, so sorry. So sorry. So it's y, and then y equals 1. Okay, so y equals 1. So just write 1 in there. Yippee! Okay, so more of the same. So hopefully you can handle that one. Then we have a little bit of story problem work. So let's try number 24. And what's the deal? So data can be modeled by the linear function. So one thing I may not have, they don't really talk about in the book, and I may not have noticed, there's the difference between a linear and a quadratic. And that's just basically the degree of your polynomial in the equation. So if you have degree 1, so if you have something like 3x plus 2, that's considered linear. Okay, because the exponent, the highest power on the exponent is a 1. Of course, we don't write it, but there it is, right? So it's a 1. If your equation has the highest exponent of 2, that's called quadratic. Okay, those phrases will come up in the homework. It'll come up later as we work through material. Maybe have to wait for 0965 to roll around, but those terms are used in this section, and I just want to make sure that's clear. Okay, so anyways, the data can be modeled with this linear function f of x equals 0.018x plus 56.29, where f of x is the average temperature, X years after 1900. Okay, complete parts A through B. So part A, find and interpret f of 40 and use the equation for f of x to identify this information as a point on the graph. So I believe they want you to use the function itself rather than to kind of, zoom in on the graph and find the point. Okay, so f of 40, you're just going to plug 40 in for x. You get 0.018 times 40 plus 56.29. Okay, so I'm going to use the internet to figure this one out. Wolfram, my favorite online calculator. You probably will find your own someday, and I could just literally write it in 0.018 times 40 plus 56.29er. Takes a long time to do any simple computations, but here we are, 57.01. Okay, so the input is the 40, the output is the 57.01. Someday I'm going to get my pen to work. Oh, there it goes. And there we go. Okay, so as an ordered pair, it's 40, 57.01. To interpret that, that means in 1940, 40 years after 1900, the average temperature, I'll just write the temperature, was 57.01. Okay. So I think that's probably the kind of thing they would want to ask here. Let's see what they ask. So as an ordered pair, first off, that's the 40, 57.01 thing they want. 40, 57.01. What's next? Interpret this, yeah. So in the year 40 years after 1900, so that's the year 1940, the average temperature was 57.01 degrees Fahrenheit. I don't know if it's right or not. I can't figure it out. Thank you for doing your job. Okay. All right. Oh, they got more questions. Does f of 40 overestimate or underestimate the actual value in the graph, and then by how much? So it's going to have to really zoom in there. At 40, it looks like it's 57 on the graph. So the value of f of 40, our value 57.01 is going to overestimate by 0.01. The value f of 40 overestimates the data in the bar graph by 0.01. Hey man, that's kind of exactly what is happening here. I mean, 40, it looks like it's at 57. Maybe it's not exactly 57, yeah. Oh, use the bar graph. Sorry. So on the left, you see in the bar graph for 1940, it's 57.1. Sorry. So you don't use you don't really know which. So from, and of course my pen stopped working. It's never one thing. It's always like an accumulation. There we go. Okay, so from the bar graph, so you're comparing to the bar graph. Bar graph. In 1940, the average temp was, so if you look at the red bar, 57.1. Okay, so yeah, it's an underestimate, actually, underestimate. And then we need to subtract these two values to get the underestimate. And so, whoops, that's, thank you for nothing, computer. So we have 57.1 minus 57.01 equals 0.09er. So 0.09. Yeah, okay, so be careful what graph you're looking at. Same sort of problem here. This time they give you two functions. One is linear, the other is quadratic. So the linear function f of x equals 1.25x plus 307. The quadratic is g of x equals 0.01x squared plus 0.6x plus 313. This time, f of x and g of x represent a concentration of pollutant x years after 1950. So x is the number of years after 1950, and then f of x and g of x is an amount of pollution. There's special units for that, parts per million in the atmosphere, stuff like that. Okay. Find and interpret f of 50. Use the information for f of x to do this and identify it as a point. So f of 50, that would be the year 2000, is equal to 1.25 times 50 plus 307. Okay, so let's zip over to my online calculator. 1.25 times 50 plus 307. And I'm getting, drum roll, 369.5. Oops. 5. As an ordered pair, 50 the input, and the output 369.5. Where are you? So 50, 369.5. Check. And the average concentration, so you want to interpret it. So the 369.5 is the average concentration parts per million in the atmosphere. So there's 369, I guess you could think little pollution particles floating about. And then the year is 50 years after 1950, right? So that'd be the year 2000. Find and interpret G of 50. So they want you to, I guess, do the same spiel with G of 50, the other function now. So G of 50 is 0.01 times 50 squared plus 0.6 times 50 plus 313. So I would go over to my online calculator. 0.01 times 50 squared. It's so helpful giving me the extra parentheses where I don't want them. Point plus 0. I'm not afraid of artificial intelligence taking over anytime soon after dealing with this kind of stuff. 313. 368 is our answer. So the ordered pair is 50, comma 368. So it's pretty close to f, the function, the f function. Let's see what the homework problem wants. They want an ordered pair first, so 50, comma 368. And don't accidentally put it in wrong. Okay, they probably want you to interpret it. So in the year 2000, there are 368 parts floating about. Okay. And now they want to know which is better. And again, look at the bar graph for the actual answer. So on the bar graph, the ordered pair 50, comma, this time we're looking at the blue bar, it's 370. And we want to know which model is closer. So a lot of math is just making up these mathematical models to make predictions about things in reality. You know, that's it. So which one worked better for us? Is it F or is it G? So the real value is 370. It looks like F is closer at 369.5. So F is linear. Okay, so notice the difference again. The linear function has an exponent of 1. Quadratic has an exponent of 2. Okay, so linear exponent 1, quadratic exponent 2. So the linear function is better. And then, oh, and then that's all they want. Okay. So this one, it looks like a plug and chug. This one kind of, so they give you a function that models the number of accidents, f of x per 50 million. It's 25, 27 rather. Okay. So the function models the number of accidents, f of x, per 50 million miles driven as a function of the driver's age, x in years, where x includes drivers from 16 to 72, inclusive, so that means it includes people age 16 and includes people 72. The graph is shown. Use the equation for f to solve the problem below. Okay. So for what values of x does the graph reach its lowest point? It looks like, just looking at the graph, the lowest point on the graph, the lowest y value is going to occur at sort of, if you think of this like a valley, it occurs at 44. So that's the x value. The y value, though, isn't clear, right? So it's somewhere in between 0 and 1200. So how do I figure that out? Well, you're just going to use the function f of x, right? So you're going to plop 44 into f of x. It'll be 0.4 times 44 squared minus 35.2 times 44 plus 964.4. So I'll go to my calculator, if I can find it in this mess. 0.4 times 44 squared minus 35.2 times 44 plus 964.4, enter, and then 190 it looks like. Okay, let me toggle back over to the homework. So it looks like 44, 90. Uh-oh, this is something silly. Use the equation f to find, oh, it's 190, sorry. Okay. So then they want you to describe what that means. So it's x is the driver's age. So that would be 44-year-old drivers are really good at driving because they only have 190 accidents per 50 million miles driven. Okay. Is that must be an, is it, okay. Oh, and these things. So these are called step functions, and they're often used for if you go to the post office. If you're envelope weighs in between 0 and 1 ounces, it's a flat cost. Okay, so just understanding how to read these things is important later on. Again, in modeling scenarios, you'll use these in electricity problems as well. It would be nice if I could zoom in on that, but let's steal the picture and kind of see what's going on. Okay, so they want to know what is f of 2.25. So how much does envelope that weighs 2.25 ounces cost? So you go on the x-axis to 2.25, 1, 2, 3, 4. So 2.25 is about right here. And then you get the corresponding y value on the graph. So you look at the blue bars. So right here, the corresponding cost is 0.75. So it's pretty self-explanatory. The only issue is at places like 2. So what happens if your envelope weighs 2 ounces? And if you look at the blue graph, it kind of looks like it's maybe $0.75 or $0.58. So 75 cents or 58 cents, which is which? Well, one, it has an open dot there. So up here, it's kind of hard to see on the picture, but it's an open dot. And below it, it's a closed dot. So you go with the one that's closed. So f of 2 is actually 58 cents, not 75 cents. Okay. And then if I had like f of 1.5, 1.5 is right here, so that would be 58 cents, right? Anything above 1 but less than or equal to 2 is going to be 58 cents. So if you have f of 1.001, that's a little to the right of 1, that's going to put you on the 58 cents track. Okay? But as soon as you hit 1, it's going to drop down because of that open dot there. Okay, so on the graph at 1, there's an open dot, but you just go with the closed dot at 41 cents. So f of 1 is actually 41 cents. Okay? So it's just a type of function. It looks kind of weird, called a stepwise function. It comes up, again, when you're modeling certain problems in electricity. And it also comes up here with post office problems. So 75 cents is going to be the cost for the weight 2.25 ounces. So a 2.25 ounce letter costs 75 cents. Okay. And then this is just another one of those. Cost of 0.3 ounces is going to be 24 cents. Okay. Those come up later on in life if you keep taking math, but we'll kind of leave them by the wayside for now. Okay, so as usual, I hope that helps, and have a good time studying, and I'll see you next time.